Let's jump right into this explainer, because we are looking at something truly mind-bending today, the discovery of superconductivity. Picture a wire, but not just any wire. Imagine one where an electrical current flows absolutely forever. Zero heat, zero energy loss, and exactly zero electrical resistance.
Seriously, if you made a loop out of this stuff and started a current, it would literally just keep flowing indefinitely. No battery required. It sounds like pure science fiction, right? Well, it is actually a completely documented reality. This is the absolute magic of superconductivity.
So let's look at part one, the illusion of friction.
To really get why this is basically magic, we have to look at the massive problem with our everyday electrical grid. In a normal conductor, like the copper wires in your walls right now, electrons zip through the material, but it's a total chaotic mess in there. They are constantly crashing into the atoms of the metal. Every single time they collide, they lose a tiny bit of energy, which turns into heat. That is electrical resistance. But in a superconductor, that chaotic bouncing just completely stops. The electrical friction doesn't just get smaller, it literally drops to zero.
Which brings us to part two, a chilling discovery.
The crazy thing is, scientists didn't exactly predict this. They kind of just stumbled into it back in 1911. Dutch physicist Heike Kamerlingh-Onnes was freezing pure mercury down to almost absolute zero, using liquid helium. We're talking unimaginably cold here. He expected the electrical resistance to just slowly, gradually fade away as things chilled. Instead, right at 4.2 Kelvin, the resistance didn't just decrease, it plummeted off a cliff. It completely vanished.
All right, moving to part three, the secret of Cooper pairs. So for decades, this impossible zero-resistance state totally baffled the brightest minds in physics. I mean, how does resistance just disappear? We didn't get an answer until 1957. A brilliant quantum explanation emerged called the BCS theory. They figured out that in these ultra-freezing conditions, electrons, which normally repel each other, actually interact with the crystal structure of the metal and team up. They bind together into what we call Cooper pairs.
And once they pair up, they completely change their behavior. They stopped acting like individual particles bouncing around like pinballs. Instead, they sync up into a single coordinated quantum wave. Because they move in perfect harmony, they just slip right past the atoms without a single crash. No collisions means no lost energy. And no lost energy? Yep, absolute zero resistance.
Now for part four, the Meissner effect. Okay, zero resistance is huge, but it's really only half the story. Superconductivity also creates this massive visual spectacle that honestly looks like a magic trick. Discovered in 1933, the Meissner effect shows us that superconductors actively hate magnetic fields. When a material transitions into a superconductor, it literally expels external magnetic fields right out of its interior. It transforms into a perfect diamagnet.
What that means in plain English is if you drop a strong magnet over a superconductor, it won't even touch it. The superconductor instantly generates surface currents to create a perfect mirror image magnetic field that pushes right back. The result? The magnet just stably floats there in midair. It's real-life levitation, an incredible anti-gravity effect happening right before your eyes.
Okay, part five, from labs to maglabs.
Now, this levitation is way more than just a cool lab trick. This specific quantum phenomenon is out there powering some of our most advanced tech right now. We use it to float high-speed maglev trains frictionlessly over their tracks, to run life-saving MRI scanners in hospitals, to steer particles in massive accelerators, and even to build quantum computers. The catch? The big bottleneck is that all of this currently requires extreme, incredibly expensive cooling to work.
But we are making massive progress. In 1986, physicists discovered a completely new class of materials, complex ceramic compounds called high-temperature superconductors. Materials like YbCO actually bumped that critical temperature up past 90 Kelvin. Now, I know 90 Kelvin still sounds absolutely freezing, but for physicists, it was a total game changer. It meant we could finally ditch the ultra-expensive liquid helium and use cheap, common liquid nitrogen for cooling instead.
And that brings us to part six, the room temperature dream.
This is literally the holy grail of modern solid-state physics. Looking at this timeline, you can see just how fast our understanding is accelerating. We went from dropping mercury into liquid helium in 1911 to cracking the quantum math of Cooper pairs to engineering complex ceramics. Right now, the global race is on to find the ultimate prize, a material that acts as a superconductor at completely normal room temperature. No extreme cooling needed whatsoever. So what happens if scientists actually crack that code? Well, it changes humanity forever. Imagine a world with power grids that ship electricity across entire continents with absolutely zero loss, giving us infinitely cheaper energy and entire new classes of technology we haven't even dreamt up yet. This is where everyday physics bends, where electrons move without limits, and where the future is actively being built. If you want to keep exploring the strangest phenomena in physics and follow along as this energy revolution unfolds, make sure to subscribe to the Code of the Universe channel. We make complex science simple. See you next time.